Okay, so as I was saying, last time we used information about the first derivative to tell us about some important features on the graph of f. So, today we're going to be starting with the second derivative, and what that's going to tell us, as you'll see in a few minutes, is going to tell us about the curvature or concavity of the graph of f. Now again, before I start, remember the following, very important statement. Everything, every concept and theorem that we've learned and will learn that relates f to f prime can be used in the same exact way to relate f prime with what? Well, f double prime. Does that make sense? And I kind of touched on that last time a little bit at the end of the hour. But anyway, so for example, we've already learned that when f prime is positive, the graph of f is increasing, right? So using that same concept, we can conclude that whenever f double prime is positive, the graph of f prime is what? Increasing. Now, what is the graph of f prime? F prime are the what? Slopes of f, right? Everybody agree? So you'd be looking for when the slopes are increasing. That's when f double prime is positive and vice versa. Are you following me? So here's what I want you to do. Again, notice that every one of these is a graph of f, okay? Just like last time. All right. And I want you to notice something. Here's f right here. And I drew a bunch of tangent lines for you as well. And what do you notice, guys? First of all, you see how the curvature curves upward, so to speak? You see that? What do you notice about the slopes in that scenario? The slopes are what? Increasing. By the way, I put approximations for the slopes like 0.3 to 0.7 and 1.2 to 1.6. So those are just approximate slopes of those tangent lines. And clearly you can see from left to right those values are increasing if you're talking about a number line. Aren't they? Yes? So whenever f is concave up, the slopes are increasing. And by the way, whenever f prime is increasing, what would you expect its derivative to be? You'd expect it to be what? Positive. So f double prime is positive whenever f is concave up. Are you with me on that? Yes? Okay? All right. Isn't this also concave up right here? Isn't it? And again, this time you got a bunch of negative slopes, but again, if you look at their approximate values that I noted for you, on the number line, when you go from negative 1.6 to negative 1.2 to negative 0.7 to negative 0.3, aren't those also increasing on a number line? Aren't they? So again, wherever f is concave up, right, how it curves upward, what's happening? F prime is increasing, but more importantly for today, what? F double prime is what again? Positive. Okay? Are you seeing that? All right, let's take an even bigger piece. Do you agree this whole graph of f here is concave up? Do you agree? Yes? Do you agree? It's all concave up. And again, if you look at all these slopes, I just put approximate slopes for all those tangent lines. When you go from that number to that number to that number to that number to that number, aren't those all increasing on a number line from left to right? Aren't they? Aren't they or not? Okay? So don't let the negatives and positives bother you. If you still look at the slopes, when you go from negative 1.6 to negative 1 to 0 to 1, again, on a number line, when you go from that number to that number to that number to that, aren't those increasing on a number line? Yes? Okay? So again, it's okay to have both positive and negative slopes and still have a situation where it's concave up throughout that whole interval. All right, now what do you notice here? F is concave what? On all of these, what do you notice? F is concave what? Down. Do you agree? Yes? Following me? And so again, what do you notice about the slopes in all three of these graphs? The slopes are all what? Decreasing. And by the way, whenever f prime is decreasing, what would you expect f double prime to be? Negative. Just like when f was decreasing, its derivative, which would be f prime, would be negative, right? Well, in this case, when f prime is decreasing, its derivative, which would be f double prime, would be negative. Does that make sense? Okay, so again, this is what I want you to remember right here. When f is concave down, f double prime is what? Negative. When f is concave up, f double prime is what? Positive. All right, now before I do an example, how are you going to remember the difference between concave up and concave down? Well, it's simple. Think of concave up like a cup, concave down like a frown. Does that help? Yeah, it works, right? Yes, so that way you won't confuse what I mean by concave up or concave down. Got it? Concave up like a cup, concave down like a frown. Good? Okay. So, let's do some examples. Again, I want to emphasize that the first example has what? This is a graph of what? What is this a graph of? F. Well, if I give you a graph of F and I say, where's F concave up or down, you can just look at it. Isn't all this concave down? Isn't it? But wait, isn't it also concave down from here to about here or so? Isn't it? Okay, so F is concave down on the intervals negative infinity to 0. And then again from about 0 to actually maybe closer to 3. Isn't this concave down? Then suddenly right about here it changes to concave up. Do you see that? Yes? And so where's it concave up? From what? 3 to infinity. Okay. All right, now wait a minute. Is everybody okay with that? All right, now I'm changing things up right away on example 2. I'm not giving you a graph of F anymore. Now I'm giving you a graph of what? F prime. But I'm asking you about what? I'm still asking you about what? F. Okay, so what are you going to look at, or what are you going to look for on the graph of F prime to determine the concavity on F? Well, whenever F prime is what? No, be careful. Be careful. Whenever F prime is increasing, F will be what? Concave what? Up. Whenever F prime is decreasing, F will be concave down. So, looking at this graph of F prime, everybody notice this is a graph of F prime? Yes? Whenever F is decreasing, like in here, isn't F decreasing there, guys? Yes? So what can you say about F there? Since F prime is decreasing, F will be what? Concave down. So F is concave down from negative infinity to about negative 1. And then where also is F prime decreasing? From about what? Here to here? Yes? And so wouldn't F also be concave down from about 3 to infinity? Are you following me? Okay, and then what about in here, guys? In here, F prime is what? Increasing. When F prime is increasing, F is concave what? Up. So from about negative 1 to 3. Is that clear? Okay, now, you couple this with what I did last time, and it can get very confusing. So you better, get it straight in your mind, what's what here. Because obviously if you start confusing all this, then the next test is going to be a disaster, which does sometimes happen if students aren't careful and they don't get it straight before test day. Is that clear? All right? All right, so let's look at example 3. This time, what am I giving you a graph of? I'm giving you a graph of what? F double prime. Does everybody see that this is a graph of F double prime? But I'm still asking you about F. So how can you look at a graph of F double prime and tell me about the concavity on F? Well, whenever F double prime is what? Positive, F will be what? Concave up. And whenever F double prime is negative, F will be concave what? Down. Okay, so in here and in here, do you agree F double prime is negative on those intervals? Do you agree? And so what would you say about F on those intervals? F is what? Concave down. So F is concave down from negative infinity to looks like negative 4 or so, and then again from 0 to 4. Following me? Okay, now what about in here? F double prime is positive in here as well as in here, isn't it? Yes? And so what do you think, guys? On those intervals, F would be concave what? What? Up. Everybody agree? So F is concave up on the intervals negative 4 to 0 and 4 to infinity. Okay. Got it? All right, so there's going to be a bunch of these. On the next test, I'm going to give you some graphs of F. I'm going to give you some graphs of F prime. I'm going to give you some graphs of F double prime, and you're going to have to tell me all about the graph of F. Okay, so we did some of this today, and we did a bunch last time as well. Didn't we at the end of the hour? But that was on determining where F is what? Increasing and decreasing, which would give you the hills and valleys on F, which are your local mins and maxes. Okay, so you should be able to tell me all kinds of things now about F when I give you a graph of F prime or maybe even F double prime. Is that clear? All right, so this leads us to our next topic, which are inflection points. An inflection point on the graph of F is simply a point where the graph changes what? Concavity. And again, so it can change from either concave down to concave up or from concave up to concave down. Either way, you'll have an inflection point on F. Is that clear? Okay. So based on everything then I've said to this point in the lesson, there are several ways to tell where F will have an inflection point. Again, suppose I give you a graph of F. Well, if I give you a graph of F, that's the easiest way because you can just look for a change in concavity. Where do you see a change in concavity here? Somewhere around what? Somewhere right around what? Maybe right around here? Yes? Right, because F goes from what? Looks like concave down to concave up. You see how the curvature changes there suddenly? So that's an inflection point at x equals 3, or you can also give me the y value. Why can't I give you the y value here? Because this is a graph of what? F. Okay. Now what if I change things up and I'll give you a graph of F prime instead? Where will F have an inflection point by looking at a graph of F prime? Whenever F prime does what? Changes from what? Increasing to decreasing or vice versa, right? So that would be what? Here and about here. Do you agree that's where F prime changes from increasing to decreasing or vice versa? Yes? And so it looks like at around, looks like F would have an inflection point somewhere around -1 and around 3. And notice, why can't I give you the y values? Why can't I give you the y values? Because I don't have a graph of F, do I? You see why I can't give the y values here? Is that clear? Okay, let's look at situation 3. This time I gave you a graph of what? F double prime. All right, so looking at a graph of F double prime, how can I pick out inflection points on F? By looking to see where F double prime does what? Changes from what? Positive to negative or negative to positive. And so that would be what? Here, here, and here. Everybody agree? All right? Yes? So F will have an inflection point at -4 something, at 0 something, and about 4 something. Again, I don't know what the y values are because I don't have a graph of F. Do you agree? We good on this? Okay, so based on this, last example here, and everything I also said on the first page, one way we can tell where F would have a possible inflection point is when our F double prime is what? 0 or what? Undefined. Okay? Okay, and so with that in mind, that leads us to what we call the second derivative test for concavity and finding inflection points as well. Okay. All right, so here we go. Now again, I don't want you to overuse that concept. What I'm saying is, if I do have an inflection point, F double prime has to be 0 or undefined. But just because F double prime is 0 or undefined does not automatically mean that F has a what? F has a what? Inflection point. Okay? It works one way but not the other. If I do have an inflection point, one of these things have to be true. Right? But just because one of these is true does not automatically mean I have an inflection point. Let me give you an example. What if this was a graph of F double prime? Isn't F double prime 0 right here? But do I have an inflection point on F? No. Why would I not have an inflection point on F?
Hello.
Hi.
Your birthday. Just come out. Yeah.
Thank you. Okay, so what's happening here? Even though f double prime is 0, f double prime does not change from positive to negative or negative to positive here, does it? So you see why sometimes you might have a 0 f double prime but not have an inflection point on f? This would have to go either what? You'd either have to have that or this situation, right? It would have to go from positive to negative or negative to positive, wouldn't it, before f would have an inflection point? Does that make sense, guys? So again, just because f double prime is 0 or undefined does not automatically mean there's an inflection point on f. Does that make sense? However, if there is an inflection point on f, then yes, f double prime would have had to been 0 or undefined. You see how it works one way but not the other? Okay? Okay, so that's another major mistake that students make that I'm trying to get you to avoid before it happens. Okay? All right. So based on everything then, this should make sense. Even though I'm presenting it to you as a step-by-step process, it really should not need to be if you understand what I've talked about for the last 15 minutes. Okay, so here's what we're going to do. To find where f is concave up or down, you're going to start, and by the way, that would also lead to inflection points, wouldn't they? Yes, maybe? Okay, and so what we're going to do is find and factor the second derivative. Okay, last time we found and factored the what? First derivative. Well, today we're going to find and factor the second derivative. Find where the f double prime is 0 or undefined, and then use those to break up your number line into test intervals. At that point, we're going to pick any nice test value in each interval, put into f double prime to see if f double prime is positive or negative, and then what will that tell us about f on those intervals? It'll tell us whether f is what? Concave up or concave what? Down, and then what will that do as well? That will also allow us to pick out the what? Inflection points on f. So you see where we're going with all this today? That's going to be the majority of what we do. Okay? All right, so here we go. First example, I typed it out for you so you don't miss anything. Just stay with me. Okay, so I'm going to give you a graph of, I'm not going to give you a graph. I should say I'm going to give you a function f of x. And I want you to find the intervals on which that function is concave up and concave down, and then use that information to find any inflection points on f. So, everybody see what we're going to do right now? Okay, so real quick, I'm sure you all can find the derivative. There it is, right? And by the way, I can factor out a what? By the way, that's not only the first derivative, that's the what? Second derivative. The first derivative is what? 4x cubed plus 6x squared, and then the derivative of that is 12x squared plus 12x. Is that clear? Okay, so this is the second derivative, and I can factor out a what? A 12 and a what? And an x. Okay, looking at that second derivative, where is that second derivative, 0 or undefined? Quick, quick, quick. Look at it. 0 or negative 1. Okay, so that's equal to 0 or undefined at what? At 0 and negative 1. Okay. All right, so what did I do then? So I started with negative infinity and I went to what? What's the first of those two numbers I run into? Negative 1. Then I picked up there and I ran into the next one, which is 0. Then I picked up there and went to what? What? Infinity? Are you following me? Okay, then what I did is I picked any nice value in here. So I just picked negative 2. In here I picked negative 0.5. And here I picked 1. I plugged them into where? I plugged them into where? Not yet. I plugged them into where? F double prime. So if I plug a negative 2 there and a negative 2 there, quickly, is F double prime negative or positive when I do that? I don't need a value. I just need to know if that product is positive or negative. Positive. Everybody agree? And therefore, what can you say about F on that interval? F is what? Concave up. Okay, then I picked the next test value and I stuck it into here and here. And what do I see? F double prime is what? Negative. And therefore, what can you say about F on that interval? F is what? Concave down. Here, if I stick in a 1, 1, 1 in there, if I stick a 1 there and a 1 there, F double prime is positive, meaning F is what? Concave up. Okay, so at this point, I have my intervals, right? Clearly, F is concave up on the intervals, what? Negative infinity to negative 1, and what? And what? 0 to infinity. Okay, now, there's a change in concavity where? Well, F changes from concave up to down where? At what? At negative 1. So F changes concavity there, okay? And so it looks like F might have an inflection point at negative 1 comma something, right? Yes? And by the way, what's happening here? F goes from what? Concave down, all of a sudden to concave what? Up. So it looks like F has another inflection point at 0 comma something. Everybody following me on that? Okay, and then now, by the way, where did I get these y values from? I plugged them into where? I plugged the x values into where? F, because these are points on F, aren't they, that we're talking about now at the end? So if I stick -1 into the original function, I get a y value of -1. Okay, if I stick 0 into my original function, I get a y value of 0. So F has inflection points at -1, -1, and at 0, 0. Are we good? Okay, can you do something like this now? Okay, well, before I let you try one, again, I just want to remind you of this. Just because you see a change in concavity does not automatically mean you have a what? Inflection point. Why not? Well, what if F looked like this and you had made a table? Wouldn't the table tell you that F goes from concave up to concave down all of a sudden at this x value? Wouldn't it? So wouldn't there appear to be an inflection point there? But in reality, there's not. There's a what? Asymptote. So even though there's a change in concavity, there's no inflection point there, is there? How can there be an inflection point if there's no point? It doesn't make sense, does it? Question. Yeah, well, that's, so what I'm saying is, if I would have plugged -1 into F and it got undefined here, then that would not be an inflection point. That's all I'm saying. Does that make sense? But since I did get a y value, it is an inflection point. Okay? All right. So go ahead and give this one a try, guys. Henry, thank you. They're actually here today. It's the first time I've ever got one of those students actually here. Obviously, you want to double and triple check your derivatives because you make one little mistake early on, the next 10 minutes of work is going to be completely wasted and incorrect, right? So you don't have that kind of time on a test. So you better double and triple check every little step in your derivatives before you continue with any table. Double and triple check everything. By the way, do not factor f prime. That just makes the second derivative harder. So when you're finding f double prime, just find f prime and stop. Do not factor f prime. Now, when you get f double prime, that's when you want to factor, right? Because that makes it easy to see where f double prime would be 0 or undefined. So think about it. Don't just, don't just memorize what I'm saying. Think about it. Think about what you're doing and what you want to do with what's in front of you. Anyone know who Kayla Krall is? Krall? Anyone know who that is? Whoever it is, they left their notebook in my room. Oh, she's a 9th grader. That's why you guys don't know her. Okay. Now again, you're definitely going to want to factor your second derivative to make it easy to pick out where that second derivative would be 0 or undefined. All right, guys. Hopefully you've got something by now, and I'm going to catch up to you. So you can keep working and just kind of peek up here every once in a while and compare it to what you have. Ready? Okay, so this is f. And so clearly I'm going to have to use the quotient rule, right, to find the first derivative. So I take the derivative of the first times the second minus the first, in brackets, times the derivative of the second, all over the second one squared, right? Okay. Now simplifying that, I get x squared plus x minus 2x squared, right? Bless you. And then those are like terms which I should definitely combine into what? Negative x squared. Okay. Okay, now don't factor that. Don't try and factor that. Just leave it alone. And then use it to find the second derivative. Ready? Okay, so here it goes. Now we're going to find the second derivative. So I have to use the quotient rule again, right? So I take the derivative of the first function, which is that, times the second function, which is all of this, minus in brackets the first function, and now times the derivative of the second function. Now when I go to take the derivative of that, don't I need the chain rule, guys? So there's the derivative of the outside. Put the inside back in the way it was, and then don't forget to finish the chain rule by multiplying by the derivative of the inside. That's a common mistake that students forget to take the derivative of the inside there. So what's the derivative of the inside there? 2x. And then all over the second one squared, right? Got it? All right, so first thing I'm going to do is just clean it up a little bit. By doing that times that. And by the way, when you have a power to a power, don't you multiply those powers, making that a 4? All right, now. You're not going to be able to pick out where this is 0 or undefined without the next couple steps. So again, once you get down to here, this is what you're going to want to do. You're going to want to look at that numerator as being this whole term minus this whole term. And what do those boxed in terms have in common that I can pull out? 2x. They both have a Well, first of all, I'll tell you this. When the first term is negative, you probably want to pull out a negative along with anything else. So I'm definitely going to pull out a negative. Can I pull anything out of the 2 and the 4? Yeah, what? A 2. I can also pull out a what? X. Anything else? Yeah, I can pull out an x squared plus 1. Don't they both have an x squared plus 1 at least to the first power? Don't they? All right, so when I pull all that out of the numerator, let's write down what's left. Ready? Okay, so if I pull all of this out of here, what am I left with? X squared plus 1. Okay. When I pull all, and then don't forget to bring down your minus. Okay. I'm just bringing down that minus. And now when I pull all of this out of this box, what am I left with? Well, first of all, if I pull out a minus, that changes that to a what? Plus. Okay, now again, what else am I going to pull out? A 2, leaving me, that 4 turns into a what when I pull out a 2? A 2. The x is gone, isn't it? And this is gone, isn't it? It's pulled out, and so what are you left with then in here? Negative x squared plus 1. Everybody agree with that? Yes? Okay, now I'm not done. I'm still not ready to pick out where this thing is 0 or undefined. So what do I got to do now? Distribute the what? The plus 2? Okay. And you get a what? A minus 2x squared and a plus 2? All right, now, is there anything I can combine in here, guys? Yeah, what can I combine those into? I can combine those, can I? And so that gives me what? A negative x squared, and then I can combine these into a what? Plus 3. Anything else here that you see I can do now? Yeah, I can cancel that with one of those, can't I? Okay, so the bottom line is this is where I end up. But agree that's where I end up? Yes? Good? Okay, so without getting down to here, you're not going to be able to pick out where this is 0 or undefined, and then you're not going to be able to finish the problem. So you see how important it is for you to be careful and find and carefully factor the derivative? Yes? Okay, so now we're ready to go. All right, so where is this derivative going to be? First of all, is it ever going to be undefined? No, because when you square something and add 1, isn't the denominator always going to be positive? By the way, that might come in handy later. That is always positive, isn't it? Isn't that always positive, the denominator? Because when you square something, it becomes positive. When you add 1, it's positive. When you cube a positive, it's positive. Agreed? Okay, so now, when is this 0? Well, when the top is 0. When's the top 0? At what? 0, right? When this is 0, which is at 0, and when this thing is at 0, right? And when is that thing at 0? Well, let's see. Yeah, don't you get plus or minus the square root of 3, guys? Yes? Okay. So what you're now going to do is you're going to use 0 and positive and negative 3 to break up your number line into test intervals. Ready? Yes? Yes or no? Okay. Okay, so starting with negative infinity, what's the first one I run into? Negative square root of 3. And then I pick up there, and what do I run into next? 0. And then I pick up there, and what do I run into next? Square root of 3. And then I pick up there and go to infinity. Everybody okay on that? So this time we have 4 test intervals, right? Yes.
So why not use x squared plus 1?
It's never, the only way this thing would be undefined is when the denominator is 0. Is x squared plus 1 ever 0? No. If it was, we would include those, right? Okay. Okay. So not only is the bottom never 0, we also note that it's always positive as well. And that'll help me when I'm filling out my table here in a second. Okay? Do you see how that's important? Okay, so here we go. Now, what did I say? You all should memorize what square root of 3 is. It's about what? It's about 1.7 or so. So what would be a nice test value in here? -2. What would be a nice test value in here? -1. What would be a nice test value in here? 1. What would be a nice test value in here? 2 or 3. Good? Yes? Okay, so here we go. So where am I going to plug -2 into now? F double prime. That's why you got to label your tables on the homework tonight. Got it? As well as on the test next week. Okay, so again, all I'm going to do is I'm going to stick -2 into here, into F double prime, and all I want to know is this whole thing positive or negative when I do that, when I stick in a -2. Well, if I stick a -2 there, let's say I get a negative times a negative, which is a positive there. -2 squared is 4. -4 plus 3 is negative, right? So I got a positive times a negative over a positive. What is that? It's a negative, isn't it? Everybody agree F double prime is negative, therefore, on that interval? Quick, yep. And therefore, F would be what? What can you say about F now? F is what? Concave what? Concave what? Down. Agreed? Okay? All right, now I'll stick a -1 into F double prime. Again, I don't need an exact value. I just want to know real quick, is F double prime positive or negative there? So if I stick a -1 there and a -1 there, see, negative times negative is a positive. -1 squared is 1 times a negative. It gives you a -1, but -1 plus 3 is positive. So you had a positive times a positive over positive. What is this? What is it? Positive. And what can you say about F on an interval if F double prime is positive on that interval? F is what? Concave what? Up. Agreed? Okay. Now, stick in a 1 real quick. Has anybody done this yet? What do you get? Quick. Everybody agree you get a negative? And if F double prime is negative on that interval, what can you say about F on that interval? F is concave what? Down. And then finally, if I stick in a 2 into F double prime, is F double prime positive or negative when I stick a 2 here and a 2 here? Quick. Let's see, that's a negative. Negative. Negative times negative is a positive or positive. Isn't it positive, guys? And if F double prime is positive on an interval, what can you say about F on that interval? Concave up. Okay, so here we go. Ready? All right, so if the question was find the intervals where F is concave up or down, wouldn't we be done right now? We'd be done, right? But I also want you to take it further and find the what? Inflection points on F. So real quick, doesn't F have a change in concavity right here from down to up at what? -square root of 3. So it looks like F might have a inflection point at what? At maybe what? -square root of 3 something. Yes? And then what about here? I have another change in concavity from up to what? Down at what? 0. So it looks like F has another inflection point at 0 something. And then what happens here? F goes from what? Concave down to concave what? To what? Concave what? Up. And so that would be maybe another inflection point at what? At what? At what? Square root of 3 comma something, right? All right, and so at this point, guys, how would I get the y values now? Plug them back into F. Aren't these inflection points on F now? So shouldn't I plug these into F to get the y values? Okay, so if I do that real quick, if I stick -square root of 3 into there, what do I get? Quick. Well, let's see, -3 squared gives you 3 plus 1 is 4. Don't I get -square root of 3 over 4 there, guys? Don't I? Yes? Okay, now stick a 0 in there and a 0 in there. What do I get for the y value? Quick. 0. And how about if you stick a positive square root of 3 in here and square root of 3 in there? What do you get? Square root of 3 over 4. By the way, what would happen if I got undefined for any of those? Then there would not be an inflection point there. Would that make sense at that particular x value? Okay. All right, so now look, we're done with that concept. I did 2 examples. I think that's more than enough for you to get the point, right? All right, now this last page is something completely different. Okay, so this is completely different. Okay, so let me just kind of summarize some things. You should now fully understand that the second derivative can tell us about the concavity on an interval, or technically at a what? Single point. Wasn't I testing it at a single point when I picked the test value in the table? Wasn't I just technically testing one point, which then led me to the whole interval conclusion, right? So you really can use it at one point if you want, can't you? To determine whether f is concave up or concave down at one particular point. Clearly I can do that, right? Yes? That's important for what I'm going to show you right now. Okay, so here we go. All right, so what I'm going to do now is I'm going to use that to, and this is where it starts to get really confusing if you're not careful. I'm going to now also use this to find local mins and maxes in a different way than I did last time. Okay? But again, this is the key to not getting confused right here. This is the key to not get confused. No matter what method I'm using, last time's method or what I'm about to show you, no matter what method I use, the bottom line is, if we're talking about where f has local mins and maxes or relative mins and maxes, which are your hills and valleys, you always start with what? You always start with what? The fact that what? F can have a possible local min or max whenever what? F what? Prime is 0 or undefined. Is that clear? You got to get that straight first. Is that clear? Okay, so now watch what happens. So all right, so here's what I'm going to do now. Ready? Okay, so I call this, and again, I don't care if you know these by name or not. As long as you know all the different methods, I'm fine. So I'm going to, or tests, whatever you want to call them. I'm going to call this the second derivative test for local mins and maxes. But you can, again, call anything you want. I don't even care if you know it by name. The name doesn't really matter as long as you know how to use it. Okay? Are you ready? So here's what we're going to do. We're going to use this to find the local mins and maxes on F. So the first thing I'm going to do is just like I did last time, which is what? Find where what? F prime is what? What? Come on. Read it. F prime is what? 0 undefined. So that's no different than last time. Now here's what's different. What I did after step 1 last time, I'm talking last week, right, is that we took those values and we used them to break up our number line into test intervals and we made the table. Isn't that what we did last time after step 1? Well, now here's where it's going to change. Instead of making a table, that's not what I'm going to do. I'm going to take the values of x that I found in step 1, in other words, wherever f prime is 0 undefined, and I'm going to find the value of the second derivative at those values. And what will that tell me? All that'll tell me is whether f is what? Concave what? Up or what? Down at one single point. Won't it? Yes? Okay, now think about it. If you know f prime is 0 or undefined, and you know therefore you can have a hill or might have a hill or valley there, right? Won't the concavity tell you whether it's a valley or a hill? Won't it? At that one particular point? Won't it? And so by finding f double prime now at that c value, if it's positive, f will have a what? Well, let me ask you this. If it's positive, f double prime is positive at that one point, what can you say about f at that one point? F is concave what? Up. Creating a what? A valley or a what? Local what? Min. Okay. Now, what if you plug that one x value into f double prime and at that one point you find that f double prime is negative? What can you say about f at that one point? F is concave what? Down, like that, wouldn't it? So that would be a what? A what? A hill, which is a what? Local max. Now, what if you get 0? Because that can happen. What if you get 0 again when you plug the x value from step 1 into f double prime? What happens then? Well, that means the test fails. Now, it doesn't mean there's no hill or valley. It just means that the test doesn't work on that particular x value. So now you're back to what then? So then you're back to what? You're back to the table method that you learned last time. Does that make sense? Right? So if the test fails, right, if you don't get a positive or negative second derivative, then you're back to what we did all of last time, which is making a table to see where the hill and valley is, if there even is a hill or valley at that particular value of C. Yes? It is easier when it works. The problem is when it doesn't work, you got to do the table anyway. Got it? So, and by the way, so you're probably saying, well, then why don't I just learn last time's method and not learn today's method? Well, it's not that simple because they are going to test you on this method on the AP exam. They're going to force you to by only giving you F double prime. Okay, so they're going to force you to do it this way. So yes, you do need to know this way as well as the way we did it last time. Okay, so I think one example will be good enough and then we'll be done. Are you with me? Okay, so here we go. All right, so now obviously I'm not doing very many examples, so absolutely you better do your homework on this or it's never going to stick. It's not going to make any sense just by going over my notes. This is one time where my notes are not enough for sure. Okay, you don't do the homework tonight, good luck. All right, so here's what we're doing. I want to use this test that I just showed you. I call it the second derivative test, but the name really doesn't matter. I'm going to use the second derivative test to find any local mins and maxes on F. Are you ready? Yes? Here we go. So, again, the fact that I'm asking you to find local mins and maxes, no matter what method you're using, what's going to be your first step? What's going to be your first step, no matter what, if I'm asking you to find where F has local or relative mins and maxes, or in other words, hills and valleys? What's going to be your first step, whether you're using today's method or last time's? First step is the same. What is it? Find where what? F prime is 0 or undefined. Isn't that where F has possible hills and valleys? Yes? Okay, so step one is to find and factor F prime. So there's F prime. Okay, then you can pull out a 4x squared. Okay, so looking at that F prime, where is that F prime 0 or undefined? Well, it's never undefined, but it will be 0 when what? When x is what? 0 or what? 3. Okay. Okay, now if this were last time, what would I do with those values? Using the break up my number line into test intervals, right? And go from there? Okay, but instead of doing that, what are you going to do now with this new method? Stick these directly into what? Into what? F double prime. Well, don't we need to find F double prime first? Okay, so using this, notice. Notice I go back to the unfactored form of F prime. That's the easiest thing to do. And so what's the derivative of 4x cubed minus 12x squared? Quick. Isn't it 12x squared minus 24x for the F double prime? And again, you really don't need to factor it if you don't want to. You can if you want, but you really don't need to. If I stick the 0 here now, if I stick a 0 there and a 0 there, what do I get for F double prime? Quick. I get 0, don't I? Yes? Okay. So what that means is that this test is not going to tell me anything yet. Okay? All right, now what if I stick 3 into here? What if I stick a 3 there and a 3 there? Again, I don't want an exact value. I just want to know if this is positive or negative. Well, 3 squared is 9 times 12 is what? Over 100, isn't it? Minus 24 times 3, which is 70-something. So clearly this is what? This is what? Positive. All right. All right, so here we go. All right, so therefore, what can we say? Just looking at 3. Since F double prime turned out to be positive, what can you say about F? Well, at 3, since F double prime is positive, at 3, you'll have what? F being concave what? Up or down at that one point? Up, creating a valley, right? Meaning F has a what? Local min. Okay, so at least we were able to figure out what's happening at 3, right? F definitely has a valley or a local min or a relative min at 3 comma something. So at least we got half of what we wanted, right? What happened though with 0 is the test didn't work. Does that mean there's not a hill or valley there? No, it just doesn't mean that. It just means the test isn't going to tell me, right, whether there is or not. You understand? So what do I got to do now? So I got to at least make a table at least around surrounding what? At least surrounding what? 0. So notice I really don't need to fill this in because I already know what's happening at 3, right? What's happening at 3? F has a what? F has a what? A local what? Min. Okay, so I don't need to fill out that part of the table. But I did need to go back and use 0 and 3 to break up my number lines into test intervals. So what you're seeing here is exactly what all our examples looked like last time. Isn't it? Doesn't that look exactly like last time's examples? Where we used where f prime is 0 or undefined to break up the number line into test intervals. And then determine whether f prime is positive or negative. And that told me whether f is increasing or decreasing. So what do you think? What's happening at 0? F goes decreasing and then decreasing again. So does f have a hill or valley at 0? Does it? No, it does not. So therefore, the table tells us that f does not have a local min or max at 0. So only thing happening with f is that f has one local extreme, and what is it? It's a local what? It's a local min at 3. Can you handle this, guys? Okay, you got some book work, and then you got these extra problems. Again, now this time I didn't give you the answer, so you're going to have to work in your groups to figure out and agree on one of the answers. So these are multiple choice. So if you look at problem 1, I give you a graph of f, and I say one of these is the correct graph of what? F prime. So you got to pick multiple choice, A, B, or C. Same thing with problem 2. Using this graph of f, which one of these is a graph of f, the correct graph of f prime? But then I start changing it up on you. Now I give you a graph of what? F prime, and I say which of these are a graph of f. So now you got to go backwards, don't you? Here I give you a graph of what? F double prime, and I'm asking you which one of these, A, B, or C, is the correct graph of f. You see how I'm switching things up on you just so you can go back and forth and get it all under control? Got it? So you absolutely must do all this, okay? Most likely I'm collecting this next time. I'm just telling you that right now. It's so important. I'm telling you right now that 90% chance that I'm collecting this from everybody on Friday. So, I'm talking about the whole assignment, book work as well. Is that clear? Okay? Okay, so you can take a break for about 3-4 minutes, and then you got quite a bit of time to get several of these done, and I want you to do that just to make sure you guys are okay with what I did today.